Let's look at a logistic regression model that allows us to predict the odds of a given binary outcome based on predictor variables. We'll go back to these data on low birth weight infants. N equals 223. We want to have a model that predicts, will a baby have this disease or not? Now, in order to make a model, we said it would be really nice to have something that looks like the probability of having this thing, this binary outcome, based on an intercept and a slope, or maybe even slopes if we add more things in. The way that this works is we change the left side of the equation. We do this thing which is called the logit function, which links the data to this idea that instead of actually predicting the outcome, we predict the log odds of the outcome, and that's logistic regression. I know every time I say the word log odds, you die a little bit inside, but stay with me. This is really cool. So the model predicts the log odds that the outcome will be equal to 1. And I know your question, you can put your hand down, what the heck are the log odds? Well, know this first. The log odds, qualitatively speaking about the log odds, is like talking about probability. If the odds go up, the probability goes up. If the odds go down, the probability goes down. If something doesn't change the log odds stays the same. So we can think about predicting this thing as like predicting probability. Odds are a little bit different. And we'll see that. Now, the model still looks linear. I want to stress that this side of the equation is the same. But now, instead of here, we're going to predict the log of the odds. This is known as the logit function. And as you read more about this, you'll see this. The log of the odds. And here we see odds. Odds are the probability of an event happening divided by the probability of the event not happening. If the forecast for tomorrow says there is a 10% chance of snow, that's your probability, and you can divide it by 1 minus your probability. That's the odds of snow tomorrow. So talking about odds is like talking about probability. Now, what we're going to see is that when we do a 1 unit increase in X, we will see how the log odds change. And how the log odds change will be able to be interpreted in terms of an odds ratio. You probably are familiar with this or will be from epidemiology, but in the odds ratio, we're going to look at some sort of odds and divide it by another sort of odds. So if you smoke, do you smoke? No, you don't smoke. Smoking's bad for you. Smoking causes lung cancer, we say. What is the odds ratio of smoking and lung cancer? Well, people who smoke have a certain odds. It's maybe big. People who don't smoke have another certain odds. It's maybe small. And if you crank out the data, whatever information you have, the odds ratio for lung cancer from smoking is something around, say, 10. It's about 10. If you smoke cigarettes, you have about 10 times the odds of getting lung cancer relative to someone who doesn't. So when the odds ratio is greater than 1, being exposed to that thing increases the odds of the outcome. And we call this a risk factor. This is the definition of a risk factor. Now, think about that again. If we go up to the top, say you look at the odds in smokers and the odds in non-smokers, if they're the same, you have the same over the same, and that's 1. So when an odds ratio is 1, it means that exposure doesn't increase your odds. Nothing's going on. We've seen this again and again. So the null value for all of this is going to be 1, that there's nothing going on. And now let's think about something that would be less than 1. Let's say exercise and diabetes. Let's say something like that. If you exercise, the odds of getting diabetes are smaller than if you don't exercise, the odds of getting diabetes. Let's say it's something like 0.5. That odds ratio is less than 1. And that means that exercise is protective against diabetes. We would say that exercise exercisers have 0.5 the odds, half the odds, or that exercise halves your odds of diabetes. Now, you could also say, what about not exercising? Well, if you take that 0.5 and you just flip it around, you could say not exercising doubles your risk for diabetes. So we're talking about ratios here. So 0.5 is as strong as 2. 0.5 and 2 are the same thing. Something halves your risk. Not doing it, it doubles your risk. Now, the cool thing about logistic regression is that when you fit the model and you get the prediction for the log odds, that beta coefficient, if you exponentiate it, you will turn it into an odds ratio for a one level increase in the predictor. This is really important, so I put all these stupid little symbols on over here. But you have to first take the anti-log and turn it into an odds ratio. And you just saw interpreting odds ratios is pretty easy. Let's see how this works in terms of these low infant babies. To fit a regression model in Stata, a logistic regression model, you use this guy, Logit. Logit Y BPD on X, birth weight. And now here's the model. The model has a intercept or a constant like we've seen before, and it has a slope for birth weight. For every 1 unit increase in birth weight, the log odds goes down 0.004. And it's significant. Birth weight is a statistically significant predictor of BPD. Now, people will freak out if you go around to them and say, the average decrease in log odds will be blah, blah, blah. What you have to do is get this into a term that makes sense for people. Everyone can understand, if you smoke, you have 10 times the odds of cancer. Everyone understands that. Hey, should I exercise? Yeah, it will cut your risk in half. Oh, I'll do that. That sounds worth it. We need to do that for this. So what we do is we exponentiate that number. Here is the model as written out from that slide in Stata. And now we get this odds ratio of 0.996. Every 1 unit increase in birth weight is associated with 0.996 times the odds of BPD. Now notice I was very careful not to imply causality there. I said this associated with. And then I got a little sloppy in this other bullet point right here. I said, if a child has a 1 gram increase in birth weight, it's not really increase. I mean, if a child has 1 gram, is this better? If a child has 1 gram higher birth weight, he has 0.996 times the odds of BPD. Statistically significant. Now, you might be thinking, well, that's might be statistically significant, but that's not very clinical relevant. I take whatever my odds are, and then I multiply those odds by 0.996. 0.996 is basically 1. Well, part of it is, think about the units here. The units are very small. Maybe we want to plug in a more meaningful value. That was for a 1 gram increase in birth. That's nothing, right? A 100 gram increase might be some meaningful change. So remember, you can plug in different values for the slope to see if there's clinical relevance. So if we do that same thing, if we take the slope and then we plug in, instead of a 1 unit increase, a 100 unit increase, we get this. Punch in the anti-log and you get 0.67. And that is for every 100, so that is 0.67 times the odds. Lower odds, it's protective. It goes down, not as like strong as like half, but it goes down. And one way people like to interpret this is if you have 0.67, you can go 100 minus 67, which is 33, and you can do this. For every 100 gram increase in birth weight, the odds of BPD decrease by 33%. Now that seems sort of meaningful. Let's try to get birth weight up. Now that sounds like I'm implying causality. Let's be careful with how we do that. But this is very nice. It shows us how to turn the logit function, that log odds, how to turn it into a sense that makes sense. This makes sense. This will make sense to anybody. Now, the good news is Stata will make the odds ratios for you. Instead of running the command logit, you can run the command logistic. And logistic, then you fit the same model, Y and X. And notice always double check this, my friends. Notice that here, Stata is explicit. I'm making the odds ratios for you. And there's that odds ratio we saw. And it's statistically significant. And you know that a confidence interval of something that's statistically significant will not include the null value. Remember, what's the null value here? The null value is 1. Is 1 in there? No. So the p-value must be less than 0.05. So you will probably use Logistic when you run these in Stata. But I had to show you the Logit thing first, just to see how it works. Now, pause it for a second and take a breath. Okay, welcome back. Multiple logistic regression is when we add additional predictor variables to the model. And they can be binary or they can be continuous. Remember, the model itself doesn't change. Y equals A plus beta 1x plus beta 2x plus beta 3x, whatever. It's the Y that changes. But the other side is after adjusting for. So I'm going to add another variable into the model, this variable, toxemia status. It's a high blood pressure that the mother can have during pregnancy. Let's see how that affects the odds of BPD. Now, we already know that birth weight is an important, significant predictor, so we better control for birth weight. To do the multiple logistic regression model, we still say logistic, and then we say Y, and then we say X1, and then we say X2, right? That's how it's written in Stata. And the model gets written out as, again, we have our constant, or the intercept, and now we see we have 2 odds ratios. Birth weight we see is about the same. It's 0.996. That hasn't changed. And in an epidemiology class, you're taught that, see how that changes. It tells you a little bit about confounding. Birth weight is a significant predictor after adjusting for toxemia. But let's take a look at toxemia. We see here, this is also a significant predictor. After adjusting for birth weight, whether or not a mom has this condition affects the probability of the baby having BPD. Now, how do we interpret it? Odds ratio equals 0.24. That's a little bit weird. This condition is protective. This condition is protective. Mothers who have toxemia have 0.24 times the risk of compared to those who don't after adjusting for birth weight. So that's what I just said. Those with toxemia have 0.24 times the odds of BPD after adjusting for birth weight. You can fit all sorts of stuff into your logistic regression model. Here I have 1, 2, 3, gestational age, it's a continuous variable. 4, whether the mom's on steroids or not, another continuous, that's a binary variable. So we get big models. And how we interpret these is after adjusting for everything else in the model, what is the change in odds when this variable X changes? We'll come back to this slide again. I love this slide. We talked before how everything that we've covered, maybe with the exception of non-parametric tests, can be fit into some overall sort of structure. And what we see today in these slides is that we have the ability to play around with the outcome. And if your outcome is categorical, you need to use logistic regression if you have a binary outcome. And you're going to generalize that eventually to this multinomial logistic regression. And you might get this, and you might get this. So you fill up, the more statistics you learn, you fill up more blanks and more holes on this table. And that's called learning.